Okay, so recombination and generation. So, so till now we assumed that there is no generation of electron or recombination of electron anywhere in my semiconductor. But that's not the reality. If you have a conduction band and a valence band, there is some band gap. The electrons in the valence band, they can get some energy from various sources. They can get, say, some thermal energy, and they can start transferring from the valence band to the conduction band. Yeah? So, when you have electrons in the conduction band and holes in the valence band, they can also recombine. Okay, so you have this constant generation of electron and hole pairs, and then they can also recombine. In equilibrium, in fact, the rate of generation becomes equal to the rate of recombination. If that's not the case, then electron density will keep increasing forever, right? If there is only generation, then electrons will keep coming from the valence band, and then they will keep going to the conduction band, and electron density will keep rising, hole density will keep rising. That's not what happens. Eventually what happens is that when you start to have a generation, your electron and hole densities will increase, but they will also start to recombine, and in equilibrium the rates will become equal. So that's the thermal generation. But you can also generate electrons with the help of light. If you shine some light on a semiconductor, so light is made up of photons. If the energy of a photon is greater than the band gap, then electron in valence band can accept that energy and move to the conduction band. And in that process also you will generate electron hole pair. Okay, so in this chapter, what we are going to study what are the rates of these generation and recombination, right? What are the processes, what are the ways in which recombination and generation can happen. So it's very, very important, and it's a very realistic thing. So all the real materials will have this, because eventually you are going to use that material at room temperature. So at least you will always have some thermal generation. And if you are trying to say study some optics, right, optical materials or photonics, so then light also comes into picture, right? If you want to make a device, say LED, so LED, so this recombination generation is going to be very crucial. Okay, so let's first talk about the recombination. Okay, so this is the process by which the electron and hole pairs will be recombined, and after they recombine, they will get destroyed, they will annihilate, right? So you have an electron, and hole is the empty state, basically empty state in the valence band. If electron fills that empty state, then there is no more a free electron, and there is no more a free hole. They will destroy themselves. So it's basically you have a broken bond, right? Remember this silicon. So hole is basically this broken bond, right? So one electron you have, but then another electron you have missing here. And now you also have an electron in the conduction band, which is moving freely. This electron, when it fulfills this vacancy here, so they will again form the bond, and in this process the free electron is gone and this hole is also gone. Okay, so they destroy themselves. So they are generated in pairs, they also destroy themselves in pairs. Okay, now recombination and generation, it can happen via several processes. So we'll try to see what kind of processes are there and which one of them is the most important one for a particular given material. So first of all, what we have is a band-to-band recombination. So as the name suggests, so you have an electron in the conduction band, and directly it jumped to the valence band and recombined with the hole, and in the process it may release some energy in the form of, say, light, in the form of photon. So that's a band to band recombination. One electron, one hole, no other particle involved. I mean, of course there is a photon involved, but no other, say, any energy level is involved, just the direct jump from EC to EV. Direct jump from the conduction band to the valence band, and they annihilate each other. In the process they release a photon. So that's called band to band recombination. So this is the first process. There can be more processes. So there can be recombination. It's also called indirect recombination, by the way. So this is a direct recombination. So electron directly recombined with the hole. But there can be a process in which the electron may indirectly recombine with the hole. So what is that process? So there can be some recombination generation centers, or in simple words, there can be some trap states within this band gap. There can be some trap states. Okay. Now, where are those trap states coming from? So you have a perfect periodic crystal, but there can be some impurities, there can be some defects, right? All of those discrete dopants, all of them, those dopants are of course intentional, right? So when you put the dopant, you want to create the electron and hole density, but in addition to the dopants, there can be some unintentional dopants also, unintentional impurity atoms. In the fabrication process, say when you are growing the silicon, so some of those impurity atoms, let's call them impurity atoms, they will enter your fabrication process, they will enter the silicon material, and now these atoms are discrete states. And usually what happens, they will give you some mid-level states. Okay, usually donor or acceptor. Where are those donor or acceptor states? So either close to the conduction band or close to the valence band. Whenever you have states close to the conduction band, say donor states, so they can donate the electron. Whenever you have acceptor states, so they can accept the electrons and they can create holes. But there can be some states which are somewhere in between, close to the mid gap. So they are called deep level states or mid gap states. There can be such traps, and they are not donating the electron, because if they have to donate the electron, say they are here, so there is a lot of energy difference. It's not easy. Okay, similarly, if they have to accept, so there is again a large difference. So these are called deep level impurities, or simply deep level energy states, right? Whenever you have discrete atoms which are not taking part in the periodic crystal, so you will have some discrete states. Okay, it can also come from the defects. If you have, say, some silicon atom you have missing and it went to some interstitial site, right? So that can also create some defect, vacancy. So the recombination generation can also happen through these defect states, okay, or these deep level states or these mid gap states. So what does it look like? So something like this. If you have EC and EV, and this is the middle of the gap, so for example, if you have a gold impurity, it gives you two states like this. Okay, if you have, say, copper, then these are the states. These are all close to the mid gap. These are not close to the conduction or the valence band. So they are called deep level states. Similarly, this manganese, chromium, iron, they can all give you some mid gap states, and these are the atoms that can enter into your process. Okay. So what happens? Electron, say I have an electron in the conduction band. Indirect recombination means electron will first transfer to any of this mid gap state, and then it will jump to the valence band. So it's like an indirect recombination. It will recombine with a hole in the valence band, but first it will transition to a mid gap state, and then it will transition to the valence band. Okay, why it is transitioning here? Why the electron is going here? Because by going here, electron can reduce its energy. Okay, and of course there is a Coulombic potential here. So whenever you have a crystal defect, so it locally creates a Coulombic potential, a Coulombic force, and that attracts the electron, and electron will fall into that state. So this process is called trapping. So whenever an electron is moving to this discrete energy states, so we will say that the electron has got trapped, and then this electron will move to the valence band and it will destroy a hole. In other words, you can also say movement of electron from conduction band to this state and this state to the valence band. But you can also say that electron moved from conduction band to the mid gap state, and a hole moved from the valence band to the mid gap state. So movement of electron from mid gap state to the valence band is equivalent to say that a hole has moved from the valence band to a mid gap state. Electron always looks for empty state. So if these states are empty, electron will jump here, and in the valence band you have empty state which are hole. So electron will again jump to those empty states. Hole looks for a filled state. Hole gets attracted to a filled state. Filled state means there is an electron, and hole is a positively charged particle, you can assume. So hole is looking for a filled state. Hole will occupy a filled state, filled by electron. So this hole sees that, oh, there is a filled state here which is occupied by an electron, and hole will get attracted to that, and when it gets attracted to that, it will transition here and it will annihilate. Okay, so the process is like this. Electron goes here, hole goes here, both of them annihilate, both of them recombine. Or in reality what is happening, electron goes here and then electron goes here. Yeah, but I mean, in terms of say mathematics of all of this, I mean the physics in terms of derivation, we will always look for this picture. This is easier to handle. Okay, the description of holes makes things easier for you, so we will always go with this picture. But in reality, this is what is happening. Now, during this transition, what can happen when electron move from here to here? It can release its energy in the form of either heat or heat, or even it can also release photons also. But usually it releases phonons. So phonon means lattice vibration, heat. That's what the phonon is. We covered the phonon in the last class, right? So electron, if it is directly coming from here to here, chances are it will release a photon. I will tell you why. Okay? It's not that it's not possible to release a phonon here. It is possible, but the chances are very low. If there is a direct band-to-band recombination, if you have a material, if you have a semiconductor material where there is a direct band-to-band recombination, chances are it will be a photon. There can be a phonon involvement also, but that is unlikely. Similarly, in a semiconductor where this process is dominating, like silicon, in silicon this is the process that dominates. So it will be mostly in the form of phonons or heat. There is one more recombination process called Auger recombination. So this is what is happening. This electron releases its energy, it collides with another electron, right? It transfers its energy to this electron. In the process, it will have to release some energy, so it will go to the conduction, the valence band. It will reduce its energy by going to the valence band. It will recombine with the hole, but this electron will get the same amount of energy and it will increase its total energy. And later on, what will happen? What will happen to this electron? Eventually there will be collisions with the lattice, so this will slowly then reduce its energy as well and will reach the bottom of the conduction band. You remember this process? So whenever the electron gains energy, it starts to lose it with several scattering mechanisms, right? So one of the important one is the phonon scattering, so or the lattice scattering. So it will start to release its energy to the lattice. So this is all heat. And why this is staircase, by the way? Staircase means it may not happen in one single process. It is happening in several. It is happening in several steps. Okay, one collision it releases some energy, then another collision it releases more energy, then another collision it releases more energy. So it releases that energy in various steps. Okay, so this is what is happening. So this is the case when you don't have any mid-gap state. So this is intrinsic Auger recombination. The same thing can also be assisted by the mid-gap state. So there can be some states, let me call those levels as ET. Capital T means trap. So these are, say, these trap states. So in this case, this electron, it does not releases an energy equal to the band gap, which was the case here. It releases only the energy which is equal to, say, the difference between EC and ET. So first this electron is going to move to this state. In this process, this will release this much amount of energy, right? That will get transferred to this electron. So you see, this is almost equal to this. Yeah, and then this electron will then jump to the valence band and recombine with the hole. So this is called extrinsic Auger recombination. Okay, so it can happen directly, it can happen indirectly through the mid gap state. If it happens directly, then this electron gets a lot of energy equal to almost the band gap, and if it happens indirectly, this will get energy less than the band gap. Okay, so this is the recombination. There are some other processes of recombination, but I won't go into that. So the most important ones I have already told you. Okay, now let's talk about the generation. So generation can also happen through similar processes. For example, what is the generation? Generation means you are creating electron hole pairs. Now it can happen through several ways. So first is the band to band generation. Say you have a electron in the valence band and you shine some light on it, and electron takes up that photonic energy and moves to the conduction band. If the energy of the photon is greater than the energy the band gap, so then it can move to the conduction band by gaining that energy. Similarly, it can get that energy from the thermal energy as well, right? It can take some thermal energy and move to the conduction band. Okay, where is the thermal energy coming from? From lattice vibration. So it interacts with some photons or something, or phonons or something, and it gets that energy and reaches the conduction band. Okay, so similar to the recombination, there can be RG center generation. So the generation can also be assisted by these mid gap levels or the trap levels. So first the electron in the valence band, it will go here, it will get some thermal energy and it will go here, and then it will get more thermal energy and it will go to the conduction band. Okay, so it can be indirectly through the RG centers as well. And then you can have this impact ionization, generation through impact ionization. So impact ionization is basically almost opposite of the Auger recombination. So in the Auger recombination, electron was releasing its energy and was going from the conduction band to the valence band. Okay, and releasing its energy to another electron, which again releases it in the form of, say, phonons. In the impact ionization, you have very high electric field. Say you have these large gradients in the conduction band and the valence band. Large gradient means you have very high electric field. Remember, that electric field is equals to 1 by q into dEc by dx. Large electric field means you have large gradient in the conduction band and the valence band. So say you have a very high energy electron, it is accelerated by the electric field, okay, and this electron knocks off an electron in the valence band. So in the process it will release its energy. So this is the high energy electron. In the process it will release its energy, but this electron will gain some energy and will reach to the conduction band. So it will create the electron hole. Okay, so it's a physically you can think that you have these silicon bonds, and in every bond you have these two electrons. So these are the electrons in the valence band here. Now you have a free electron which is in the conduction band. This is the electron, okay, I'm talking about. So this is a high energy electron accelerated by the electric field, say, at very high electric field. So this electron knocks off this electron in the band because it has a very high energy, so it can break this bond. So in this process what will happen, this electron will reach the conduction band here, and in the process there will be a hole creation. So this is generation via impact ionization. It's opposite of the Auger recombination. In the Auger recombination you are coming from the conduction band to the valence band. Here you are. So in the Auger recombination what was happening, there was a high energy electron, but that was releasing its energy to another electron. Okay, even if there is no high energy electron in the Auger recombination, it can still happen. Why? Remember the bands were flat there. I did not made these slanted bands there. So even if you don't have, say, high electric field, it can still happen. So let me go back there. So this, yeah, even if it simply goes from here to here, right? Earlier what was happening in direct band to band recombination, it was releasing that energy in the form of, say, photon. But now that energy can also be used to accelerate another electron, right? Even if it is not at a very high energy state, say it is close to the conduction band, still it can simply move to the valence band. It will release an energy which is equivalent to, say, the band gap, roughly more, a little more than that in fact, and that energy will be transferred here, and this will go to the higher energy, and then it will be released in the form of phonons. Okay, let's start. So let's talk about direct and indirect band semiconductors. We have already seen it at that time. We did not discuss that in detail. So what is the direct band semiconductor? Direct band semiconductor means you have conduction band and the valence band. Conduction band minimum and the valence band maximum both are at the same value of the wave vector, k equal to 0. So if the valence band maximum, conduction band minimum are both at k equal to 0, then we call that semiconductor as direct band semiconductor. If the valence band maximum is at k equal to 0 and the conduction band minimum is at k not equal to 0, then we call that as indirect band semiconductor. Do you remember for the valence band maximum was always at the gamma point. Remember the gamma point, there was gamma point, X point, L point and all of that. When we are talking about the constant energy surfaces and the Brillouin zone. So gamma point is the center. Gamma point is the center. Yeah, the Brillouin zone center is the gamma point. And all the valence band had, be it for the gallium arsenide, germanium, silicon, all of them had the valence band maximum at k equal to 0. But conduction band minimum for the gallium arsenide, if you remember, that was at k equal to 0, but for, say, silicon and germanium it was not at k equal to 0. So the situation was like this. So for a direct band gap semiconductor, you have a band, you have an EK diagram. So at k equal to 0, conduction band, valence band maximum and conduction band minimum, they align, so that's a direct band gap. And this is the case for the gallium arsenide. For indirect band semiconductor, valence band maximum at k equal to 0, but conduction band minimum, say there are two minimum, but this is the minimum of the conduction band. This is the least energy least energy possible in the conduction band. So this will be my conduction band edge. So this is the EC point and this is EB point, but they are not at the same K. So this is at a higher K. Such semiconductor is called indirect band semiconductor, and the example is silicon and germanium. If you remember their EK diagrams, they were not at K equal to 0. Okay, so so this has a role to play. If the K of valence band and conduction band are aligned or not aligned, that plays a role. That plays a role in the recombination and generation. What kind of particle an electron can interact with, it will depend upon if their K is aligned or not. So what is K? K is crystal momentum. Yes? And if it is momentum, it has to follow the conservation of momentum as well. Yeah? Initial momentum of all the particles must be equal to the final momentum of all the particles. Yeah? If an electron is interacting with some other particle, say a photon or a phonon, the momentum has to be conserved. Plus the energy has to be conserved. So there are two basically restrictions: energy conservation, momentum conservation. And depending upon what is the particle and what type of material I have, is it a direct band or indirect band gap semiconductor, your mechanism for the recombination generation can change. Okay, so let's talk about electron and photon interaction. Let's see that. Now photon is a particle which has zero rest mass. Yes? Photon is basically light, quanta of light. So photon is a particle with zero effective zero mass, zero rest mass, and it moves with the speed of light, but it carries a very little momentum. Let's see what is the momentum it carries, the photon. So let's talk about a case of a photon which is useful for us. So what kind of photon is useful for us? What kind of photon is important for us? A photon which can make the electron from the valence band go in the conduction band. A photon which has an energy higher than the band gap. That's the kind of photon we are talking about. Yes? So we can assume that the energy of the photon that we need is going to be approximately equal to the band gap energy. It should be larger than that, but just to get an idea of the numbers, let's assume that the energy of the photon is equal to the band gap, and let's assume the band gap is 1.42 electron, which 42 electron volt, which is the case for gallium arsenide. Gallium arsenide is a 1.42 electron volt, the band gap. Now to have this much of energy, let's calculate what is going to be the wavelength. So E is equals to hc by lambda. Everyone remembers this relation for a photon, right? The energy of the photon is h into c by lambda. C is the speed of light, lambda is the wavelength, and from here you can calculate what is my lambda. So lambda comes out to be 0.87 micrometer. So the wavelength is in the micrometer range. Yeah. So what will be the photon wave vector? Wave vector is basically the momentum, right? So h bar into k, that gives you the momentum. So if I have a wave vector, I can easily calculate the momentum. So let's just to make it easy, just to make the comparison easier, let's talk in terms of the wave vector instead of the momentum, because it's simply a multiplication factor. H bar into k will give you the momentum. So the photon wave vector is going to be 2 pi by lambda. Okay, so it will not be here. So it will be 2 pi by lambda. Yeah, that's the wave vector. Let's compare this photon wave vector with the wave vector of electron. Okay, so what is the order of the wave vector of electron? Let's see that. So the order of wave vector of an electron, say for silicon, where is the conduction band of the silicon? So you have this k equal to 0, right? And then you have this some EC here, some EV here. So this is at some K. I'm saying what is this value of K? Do you remember? So all the K states can be confined to the Brillouin zone, first Brillouin zone. We know that. How do we get the Brillouin zone? From the concept of reciprocal lattice. Yes? So if your initial lattice, if your direct lattice has a unit cell of say, unit cell length is say A. In case of say silicon, the unit cell length is say A. So what is the length of the unit cell in the reciprocal lattice? So what is the length of that Brillouin zone? Brillouin zone lattice of the order of 2 pi by A. Exactly it is 4 pi by A, but half of it is 2 pi by A. Okay, so the K vector, so this thing, when you move from say this gamma point to the X point, so X point is the last point of the Brillouin zone. So this whole length is actually 2 pi by A, this thing. And this is this valley for silicon, if I remember it correctly, this is close to this, I think it is 0.8 times 2 pi by A or something. Okay, so let's not talk about fractions and all. So let's assume that it is 2 pi by A. So maximum K vector that an electron can have is 2 pi by A or of this order. So I have 2 pi by A for the electron. Compare these two. H bar K is the momentum. Now compare the momentum of these. So K is equals to 2 pi by lambda and K of electron is equals to 2 pi by A. Lambda is in the range of micrometer. What is the range of this A? What is the range of this A? Unit cell. What is the unit cell length for silicon? 5.43 angstrom. Of the order of 10 to the power minus 10. This is of the order of 10 to the power minus 6. Which one will be larger? Wave vector of electron is going to be much larger than the wave vector of the photon. So the momentum of the photon is much smaller than the crystal momentum of an electron. Okay, at least for an electron which is there in the conduction band of a silicon. So this, when an electron is say interacting with a photon, say I have an electron and I have a photon. When these particles interact with each other, so there is an electron moving like this and there is a photon coming like this, say. Initial momentum has to be equal to the final momentum. But this carries very little momentum compared to this. What will happen? Will it alter the momentum of this? After the interaction, electron will still move like this, almost in the same direction with the same momentum roughly. Okay, so if an electron say absorbs a photon or releases a photon, the change in its momentum is very little because the K of photon is much smaller than the K of electron. So in that case, how will a photon absorption or emission look like in EK diagram? Can anyone tell me? If I have say this EK diagram and this electron is say absorbing a photon and it is moving from here to here, or you can say an electron from here to here is coming from here to here, I mean conduction band to band, anything is possible, and it is releasing a photon. So how will it look like? It will almost be straight. So why straight? Look at the K values. So electron has say some k here, yes, but the k value of this electron will not change even after the interaction with the photon. So this k value, and after the transition it will be almost at the same k value. So it is almost a vertical line, the photon interaction in the EK diagram. Okay, so let me show it with the better figure. So this is the thing. See, I have a electron which is coming from conduction band to the valence band, and it is releasing a photon. So this jump is going to be almost straight, because the k initial and k final will be almost equal. So this is how electron and photon interact. Now assume that I don't have a semiconductor which is like this. So this is a direct band gap semiconductor, you know, k equal to 0 and k equal to 0, conduction band minimum, valence band maximum, they are aligned in this case, right? So this vertical thing is possible. Assume if I had this valley somewhere here, as in the case of silicon, will a photon and electron transition, will that be probable? Can I have an electron which can directly transition like this? So k of electron is a large value here, and k of the final valence band is very small value. So the difference in the momentum required is huge. It is of the order of 2 pi by a. Can my photon give that much momentum? No, it carries a very little momentum. When it collides with the electron, it almost does not change its momentum. So this electron can transition here, but there is no state here, because you know, with the photon interaction it can just go vertically. It cannot go this horizontally. So for silicon, will such a transition be probable? No. To cause that much change in momentum, you will require a very, very high energy photon. Let me see. So this is hc by lambda is equals to energy, inversely proportional. So if you increase the energy of the photon, a very, very high energy photon if you have, then maybe your lambda will reduce, right? Lambda and energy are inversely proportional. Lambda goes here, energy goes here. So if E is very, very large, lambda becomes comparable to say nanometer or so, but that's not usually the case. Yeah, that's not the case of the photon which has this much amount of energy. Yeah. Okay, so those are not the photons we will usually encounter, right? So you are talking about very high energy photons. Okay, and those special kind of photons won't be available, say, if you simply have your silicon device just sitting at room temperature in a normal environment. No. But this type of transition can definitely happen in a direct band gap semiconductor. It's a very easy. It's so feasible for a direct band gap semiconductor. You don't require a change in momentum, you just require a change in energy. And that's exactly what the photon does. That's exactly what the photon does. So for a direct band gap semiconductor, this process is very, very feasible. Okay? Plus, there is no mid-level state or anything, right? So it only requires one electron, one photon. Okay? So it's a very simple process. Simpler the process, its probability will increase. If you make the process complex, you will see that the probabilities of such processes will decrease. This type of transition is possible in an indirect band gap semiconductor as well, but it cannot be possible just via photon. You will have to involve some other particle also. So yes, there is a possibility that electron can move from here to here, but not directly with the help of photon. It will have to involve some kind of other particle as well. So we'll see that. But this is possible for a direct band gap semiconductor. For example, gallium arsenide. Okay, Now gallium arsenide, because it is possible, so electron can jump from here to here and it can release the photon, and photon is light. So direct band gap semiconductors are going to be very useful for making these photonic devices like LED. LED is made up of gallium arsenide. Why? Because it can release the energy in the form of light. It's feasible. Silicon will not give you light. It will not, because this process is not feasible. Silicon will give you heat mostly. You'll see that. So next is that electron phonon interactions. What is phonon? Phonon is lattice vibration, and lattice vibration we can discretize that, right, in the packets of energy called phonon. Okay. So what happens when an electron and a phonon interacts? So phonon does carry a good amount of momentum, but the energy carried by the phonon, that is very small. What is the range of energy carried by a phonon? I told you in the last class. What's the range of energy? I made that omega versus k diagram. Remember that? So this omega versus k. Looked like this, then like this. So if I talk about h bar omega, right, not just the omega, so this energy, these are not very high energies. These are small energies. So these are the energies in the tens of milli electron volts. So let me show you the exact diagram for, say, silicon. Okay, so it's going to be in the range of 10 to 50 milli electron volt, the energy of the phonon. So this is an example for silicon, right? So there can be several branches. So T means transverse, L means longitudinal. If the atoms are moving like this, so it's like a longitudinal wave. If the atoms are moving like this, it's a transverse wave. Both type of waves can exist in a lattice, right? The electron can vibrate, the atoms can vibrate like this, atoms can vibrate like this. Okay, and depending upon what kind of mode you have, transverse or longitudinal, you can have different branches. So this branch and this branch is for the longitudinal, this branch and this branch is for transverse. Any of the branch you take, so any point in this branch, say if I pick this one, so this is a phonon which has an energy of frequency times the Planck's constant. Okay, so and what is the wave vector? Wave vector is somewhere here. Okay, and it's of the same order as you have say the wave vector for an electron, so of the order of say 2 pi by a or so. So it's the same thing. Okay, so remember I told you this is also pi by a and minus pi by a, so it's the same. These are the same, right? The wave vector is similar, so it can carry a lot of momentum, but the energy is small. It's simply 30 milli electron volt or maximum. Let's talk about the optical phonons. So these are acoustic phonons. This branch is acoustic. This is optical. A means acoustic, O means optical. For optical phonon, even optical phonons are high energy phonons, but even for them the energy is in the range of 50 to 60 milli electron. So that's the maximum you can get. Now this energy, if you compare with the band gap of the silicon or any material that is of interest, it's around 1 electron volt at least, right? Silicon is 1.12, gallium arsenide is 1.42. So you have 1 electron volt, then you have simply 50 milli electron volt. So the energy of the phonon is very, very small. It can change the momentum by a large amount, but it cannot change the energy by a large amount. One single phonon. Okay, one single phonon cannot do that. So how will the phonon interaction look like in the EK diagram? It can change the momentum, it can change the k vector. When electron say collides with a phonon, the momentum of the electron will change. It will change by a large amount, but the energy of the electron will not change much, because even after the absorption of the phonon or emission of the phonon, the energy difference is going to be small, 50 milli-electron volt or so. So that's why this type of interaction is going to look horizontal in the EK diagram, almost horizontal, because the change in energy of the electron after the interaction with the phonon, it is much smaller than the band gap. So this small change compared to this large gap will look very small. Okay, now let's talk about this indirect band gap semiconductor, and let's see, can there be a band to band recombination. So I have an electron in an indirect band semiconductor like silicon. So conduction band minimum, valence band maximum, they are not aligned at the same K. So this electron, if it wants to do this band to band transition means there cannot be an involvement of any traps or anything like that. Any mid gap states won't be there. Photon or phonon can be there, but no mid gap states. So for that, what does it do? We know that photon cannot be directly emitted because it cannot change the momentum, but phonon can. So first electron interacts with a phonon that changes its momentum to a smaller value of K. Okay, after that electron, because now it is at a smaller value of K, right? So in this process the energy of the electron changes by a very small amount. Now the electron still has to go from here to here, but this amount of energy is large, so a phonon cannot create such an energy difference. Plus if you interact with a phonon, it will change the momentum to some other value. I mean, it will change the momentum by a large value, maybe here or here, right? So now electron cannot interact with a phonon. Now electron interacts with a photon. It releases a photon, loses its energy without changing the momentum in this process. So momentum remains the same almost, but it can change the energy by a large amount. So it's a two-way process. First, electron has to find a phonon which can change its momentum. Then after the momentum of the electron changes, it has to release a photon, and then it will go back to it will come back to the valence band. So because of the involved nature of this process, first so it's like a two-step. First electron has to interact with the phonon, then it has to release a photon. So if you make the process complicated and involve more particles, so it has three particles involvement: electron, phonon, photon. This process is much more complicated than your simple band-to-band recombination process in a direct band gap semiconductor. Electron just had to release a photon. But because of the complex nature of the process and involvement of three particles, this process becomes very less probable. See, there are several processes and they are occurring simultaneously. It's not like one happens and the other doesn't happen. It's about which one is the dominant one. All of them are happening. Band-to-band recombination is happening. So this is happening, but the rate at which this process is happening is very low. The probability is very low. So indirect band gap semiconductors, they will not prefer this process. So what they will prefer in an indirect band gap semiconductor, so they will prefer to jump through mid gap states. So there are these mid gap states. Okay. So electron, because now you have created a mid gap state, so electron can first go from here to here, okay, and then they can come to the valence band. Because if you have mid gap states like this, so this reduces the amount of energy change that is required. Okay, and that process occurs mostly via phonons. Okay, so this is something I've written, so you can go through the notes. Okay. So in an indirect band semiconductor, recombination will be dominated by RG center process. RG center means indirect recombination via some mid gap states, and in a direct one you have this direct jumps. Even sometimes in a direct band semiconductor, this process, so the RG center process, that is also happening in a direct band gap semiconductor, and in some situation, even in a direct band semiconductor, this RG center process can dominate. So it's all relative. Which one has more probability of happening, which one has a more rate, so that will be dominant. Okay, so now we have understood the interaction between electron photon, electron phonon. Let's try to do some mathematics. Let's try to derive some relations for different processes. So let's start with the simplest one. Let's start with direct band to band recombination and generation. Then we will move to indirect one. So direct one is very easy. So direct one means that you have, if you want to generate a electron hole, so in a direct recombination generation, in thermal equilibrium, so what will happen? There will be some electrons that are going from here to here, yes, and there are some electrons which are going from here to here. And in thermal equilibrium, the generation rate will be equal to the recombination rate. The rate at which the electron hole pairs are being generated will be equal to the rate at which they are being annihilated, the recombination rate. Okay, so let's try to see what are these rates and what do they depend on. What about the generation? If I have said simple thermal generation, no light, nothing, right? Simple thermal generation via band to band generation. So electron gets thermal energy, reaches the conduction band. So what will it depend upon? What do you think it will depend on? It will depend upon the temperature. If you increase the temperature, the rate will increase. If you decrease the temperature, the rate will decrease. Thermal energy will decrease. So it will only depend upon the temperature. Plus the generation rate for, say, hole and electron, it will be exactly equal because they are created in pairs. If you are creating the holes, you are simultaneously also creating electrons. So the generation rate for electron and hole will be equal. Similarly, the recombination rate also will be equal. I mean, the rate at which they are recombining. So when they recombine, they annihilate each other. So both of them are gone simultaneously. Okay, so their recombination rates are also equal. But let's talk about the generation first. So generation rate of the electron for a band to band direct generation, so it will be Gn naught equal to Gp naught. Naught means equilibrium. Whenever I am putting a naught here, so it means it is equilibrium situation. So in equilibrium, Gn naught equal to Gp naught. So this electron generation rate will be equal to the whole generation rate. Let me call them combinedly as some G naught, and this is going to be a function of temperature. Totally going to be a function of temperature. Now what about the recombination? What about the recombination? Recombination rate of electron and hole are equal, but what do they depend on? What does the recombination depend on? Recombination depends upon the availability of carriers and the availability of empty states. Say this electron wants to come here. So the rate is going to be proportional to, the rate of recombination is going to be proportional to the number of available electrons here and the number of available states here. What is the number of electrons available here? That will be given by the concentration of electrons. And what is the number of empty states that are available here? That will be given by the concentration of holes, vacant states. So this rate is going to be proportional to the product of electron concentration and hole concentration. And because we are in equilibrium, so they will be proportional to the equilibrium electron and equilibrium hole concentrations. Equilibrium means when there is no current. Okay, so Rn naught is equals to Rp naught is equals to alpha R is the constant of proportionality R for recombination times N naught times P naught. In general, we can assume that this is a function of temperature. Now, what will happen? So, in equilibrium, the generation rate, the net generation rate, and the net recombination rate, they have to be equal. Yes, in thermal equilibrium, the rate at which these are being created will be equal to the rate at which they are being destroyed. So, in equilibrium, G naught has to be equal to R naught. If G naught is equals to R naught, it means you can equate this thing to this thing, right? So then N naught P naught will be equal to alpha G divided by alpha R. And I know that this alpha G is totally a function of temperature. So it means N naught into P naught in thermal equilibrium is equals to a constant which is totally a function of temperature. Of course, and material also, right? It will depend upon material constants as well. Okay, and we know that N naught into P naught is equals to Ni square. We already know that. Yeah, but this is just another way of proving that N into P remains constant for thermal equilibrium. And in this, I did not assume that it is intrinsic semiconductor and extrinsic semiconductor. It has dopant or not. It can have dopant. It cannot. It may not have dopant. For any situation, this will hold. N into P in equilibrium will be equal to some constant which is a function of temperature, and we know that this is equals to Ni square. This is also called law of mass action. Now let's talk about a case which is not equilibrium. Let's talk about a non-equilibrium case. Now what happens, say, so this is thermal equilibrium, right? So electrons are getting generated and they are recombining. So this is thermal equilibrium. You have thermal equilibrium concentration of electron here, thermal equilibrium concentration of holes here. But you can create a non-equilibrium situations by either applying some kind of a bias, some kind of a voltage across the semiconductor, or you can also create a non-equilibrium situation by shining some light, shining some radiation on the semiconductor. So whenever you shine some radiation on the semiconductor, extra electron and hole pairs can be generated then, which will be different from the equilibrium concentration, and that will disturb the equilibrium. Okay, so you can create these perturbations using either light, or you can apply some kind of bias. So let's try to see those kind of situations. So direct band-to-band recombination, let's see. When you have a non-equilibrium situation. So say I shine a light on a semiconductor, right? And if h nu is the energy of the photon, is greater than the band gap, so this will create additional electrons in the conduction band and additional holes in the valence band. Yes? And this will be on top of the thermally generated electron hole pair. So thermal generation is still going on, that is there, but on top of the thermal generation you create this extra electron and hole density. Okay, so like this. Yeah, so this is thermally generated N naught and P naught, but these are extra things. So you have some delta N and you have some delta P, and the total generation rate till the time you are shining the light is thermal generation rate plus the generation rate due to light. L means light. So total generation rate will be the sum of the thermal generation plus generation through light. Okay, now let's turn off the light. I generated these excess electrons and suddenly now I switch off the light. So as soon as I switch off the light, this GL will be gone. Immediately this GL will be gone, no further generation because of the light, but you still have these excess electrons whose, the total concentration of electron is not equal to the equilibrium. So this system is still in non-equilibrium situation. It has excess electrons, it has excess holes. And any system, if you leave that system in non-equilibrium situation, it will try to come back to the equilibrium by releasing some energy. Okay, so what will happen? So if you turn off the light, so G will become G naught, and just after you turn off the light, there will be excess concentration of electrons, say delta N, and excess hole concentration, say delta P. This is on top of N naught and P naught. Total concentration is N naught plus delta N and P naught plus delta P. N naught plus delta N for electrons, P naught plus delta P for holes. That's the total concentration right now, just after you switch off the light. And of course, because electrons and holes are created in pairs, so whatever you have created through light, delta N must be equal to delta P. Yes? Because they are created in pairs. Okay. So what will be equal to the NP? Why I am talking about NP? Because the recombination depends upon the product of N and P. Because now you have excess electrons here and excess holes here, so the recombination rate will increase. It will be more than the recombination rate that was there in the equilibrium. Yes, because you have created these extra concentrations. So N into P will be N naught plus delta N into P naught plus delta P, and this will be greater than N naught times P naught. N naught times P naught gives you the recombination rate in equilibrium. This is the recombination rate in non-equilibrium, and this is greater than, so there is more recombination. Okay, what will be the net rate of change of electron concentration in the conduction band? Can you tell me now? Don't forget this G naught. So G naught is the rate at which they are being thermally generated, and it is always there. At any temperature, capital T, if you have non-zero temperature, there will always be some generation. But there is also a recombination which is different from the equilibrium recombination. So what will be the net rate of change of electron concentration? dN by dt is equals to dP by dt. By the way, why are they equal? Because electrons and holes are created in pairs. So rate of change of electron concentration will be equal to the rate of change of hole concentration. Okay. They will also be equal to d of delta P by dt and d of delta N by dt. Why? What is N? N is equals to N naught plus delta N. If I take a derivative dN by dt, this N naught is a constant, it's some number, right? So it will give me d delta N by dt. So either you want to write in terms of excess holes or excess electrons, or you want to write in terms of the total electrons and total holes. So it's up to you. But rate of change of excess electron concentration or full electron concentration will be equal to the generation rate minus recombination rate. The rate at which they are being generated minus the rate at which they are being recombined. Okay. Now this generation rate, this is thermal generation rate. The thermal generation rate, it only depends upon temperature. Whatever is happening to your electron and hole concentration, it has nothing to do with that. It will only depend upon temperature. So that's why I don't have a G here. G is equals to G naught. So I wrote G naught here, right? Because G is equals to G naught. Minus R. R is not equal to R naught, by the way. R is different because NP is greater than N naught P naught. So what is R? So by the way, this G naught, because this does not change, so this value will still be equal to the value of G naught which was in equilibrium. What was the value of G naught in equilibrium? It was alpha R into N naught into P naught, because at that time recombination rate was equal to the generation rate. So we can still use that, minus alpha R into NP, which is the recombination rate now. Any confusion in this? So this is a constant quantity dependent upon temperature. This quantity changes with N and P as well as temperature. Take this alpha R out. So this will become N naught into P naught is equals to Ni square minus N into P. N is N naught plus delta N, P is P naught plus delta P. If you rearrange the terms, so you will get alpha R is equals to Ni square minus N naught P naught minus all of these terms. Here I know that Ni square is equals to N naught P naught. So this is gonna get cancelled. So what will I be left with? So I will be left with this. Rate of change of excess electron or hole concentration is equals to minus alpha r. You have products like N naught into delta P, delta N into P naught plus delta N into delta P. Now we are going to make an approximation. I'm going to make an approximation that this delta N and delta P, they are small. If I assume that my delta N is much smaller than N naught and delta P is much smaller than P naught. So this is called low level injection. Low level injection means delta N and delta P are small. Delta N is much smaller than N naught, delta P is much smaller than P naught. Okay, for say an N-type material, N naught is going to be the concentration of electron. It's going to be very large. Yeah, it's going to be 10 to the power 15, 16, 17 per centimeter cube. So compared to that, we are assuming that the delta N is much smaller. Similarly, compared to P naught, I am assuming my delta P is much smaller. Okay, if I do that, so what do I get? Say I have an N-type material. N-type material means N naught is much greater than P naught. Yes, N-type material. So this N naught is going to be much greater than the P naught. So all the terms which have this P naught, they become negligible compared to the N naught term. So see, there is a delta P and delta N. Delta P is equals to delta N. We know that. So this is a term which is N naught into delta P, and this is a term which is P naught into delta P. These two. So which one is higher? This, for an N-type material. Okay, so I can neglect this term. Plus this term is a product of two small terms, delta N and delta P. So the product will be even smaller. I can neglect this as well. Delta N, delta P are equal, so this is basically your delta P square. And delta P is very small. So I can neglect it, and what do I get then? I get this. So d delta P by dt, I mean equal to d delta N by dt also, I haven't written it, is equals to what will happen? Minus alpha r into N naught into delta P. Let me call this thing alpha r into N naught, inverse of that as some tau P. So this has a dimension of inverse of time. If you check it, so this will have a dimension of inverse of time, because you have concentration here, you have time here, so there should be a time here for the dimensional consistency. So this has to have a dimension of 1 over time. Let me call this as some inverse of this as some tau P. Tau P is some kind of a time constant. Okay, so d delta P by dt is equals to minus delta P by tau P. Delta P is the excess hole concentration, means the concentration now minus the concentration at equilibrium, P minus P naught. That's what this delta P is. And this tau P is equals to 1 upon alpha r into N naught. This is called recombination lifetime, or it is sometimes also called minority carrier lifetime. See, why I am talking about the minority carrier, not the majority carrier. See, you have an N-type material, and now you generate these extra electrons and extra holes. Which one will be impacted more? The hole concentration or the electron concentration? See, N naught is already very large. If you add some delta N in an N-type material, this is still N naught. Assuming that I am talking about low level injection. N naught is, delta N is much smaller than N naught. So this is approximately N naught. But you have hole concentration which is P naught. P naught is already very small. what is the order of P naught? P naught is equals to N naught into P naught equal to Ni square. So this is Ni square divided by N naught. Say I have a doping of say 10 to the power 16 per centimeter cube. Okay, so N naught is going to be approximately 10 to the power 16. And what is the order of this? Ni is 10 to the power 10. 10 to the power 20 divided by 10 to the power 16 gives me 10 to the power 4 per centimeter cube. Very small, smaller than the intrinsic carrier concentration. So this P naught is already very small. And if you add a delta P here, it is a significant change, even if the delta P is small. So that's why I'm talking only about the minority. That's why I'm calling this tau as the minority carrier lifetime. Why lifetime? Because look at this. So d delta P by dt is equals to minus delta P by tau. I can integrate this, right? And after the integration, I will get something like this. Okay, so take this delta P down here and take this dt here and integrate. So that will be log of delta P. Yes. So this will give me log of delta P is equals to minus some t into tau P. And what do I get? So plus some integration constant. And integration constant, if I calculate, at t equal to 0, say my delta P is delta P naught. Okay, so what will happen? T equal to 0 will become equal to 0 here. C log of delta P naught. So what do I get? Log of delta P is equals to minus t tau P plus log of delta P naught. Take it on the left side. So this will be minus delta P by delta P naught equal to minus t tau P, which implies precisely this. Right, take the exponential both sides, so the log will be gone. Delta P by delta P naught will be equal to e to the power minus t by tau P. So that's what you get here. Now why this is some kind of a lifetime? Because look at the concentration of holes, excess holes. It changes as an exponential of minus t by tau. So this is some kind of a time constant, right? This is the mean time, you can say it's a mean time after which the hole will disappear. So hole is recombining with the electron, right? Electrons are coming from the conduction band, recombining with the hole. And these holes are in the sea of these majority carriers. So say because you have n-type material, there are a lot of electrons and small fraction of holes. And these small fraction of holes, you just send them to a sea of, a big sea of these majority carriers, electrons, and as they move, they recombine. Now some recombine very quickly, some will recombine very later. It's not that all of them are recombining together. No, that's not how it works. It's a statistical process. Some of them will combine very early, some of them will combine very late, but on average, you can say each hole recombines after the time tau P. You can actually calculate that. If you calculate the average time, the lifetime of a hole, average lifetime of a hole, minority hole, that will become equal to tau P. I'm not doing that derivation, but you can calculate that. You can actually calculate the average, it will come out to be tau P. Okay, so that's the physical interpretation of this tau. After tau, it will disappear. Okay. So similarly, if we have if we have a p-type material, right, and we assume that there is a low level injection, and this p naught of course will be much greater than the n naught in that case for a p-type material. Yes. So you will neglect all the terms which have n naught. So this is neglected and you will be left with this term, and this is already small, so you can neglect it. So what will happen? Now because I am talking about a p-type material, so what are the minority carriers here? N. So I'll talk about d delta n by dt. It is also equal to d delta p by dt, but doesn't matter, the whole concentration doesn't matter, right? Electron concentration contributed by the photons, that will matter. So this is minus alpha r into p naught into delta n. Let me call the inverse of that as tau n, and this is equals to minus delta n by tau n. Tau n is called lifetime of electron. It's also some kind of a minority carrier lifetime. What happens if I have a material which has significant concentration of electron and hole? So the material is not, say, n type and not p type. It says somewhere in between. I mean, I have a significant concentration of electron and significant concentration of holes. If I have a situation like this, then I can't assume P naught is much greater than N naught or N naught is much greater than P naught. In that case, I will have to keep these both terms. Both of these terms I will have to keep. But because I have a low level injection, I can still neglect this term. Delta N into delta P is delta P square or delta N square. That will still be small. So if I just neglect this term, I will be left with these two products. Okay. And of course, this delta P and delta N are equal, so I can take it out. Let me call both of them as delta N, right? So let me take this delta N out, and this will be minus alpha into N naught plus P naught, and I can write it as minus delta N by tau, or I could have also written it as minus delta P by tau because both of them are equal, and tau in this case is inverse of alpha into N naught plus P naught. So this is a more generic case. Now, what do N naught and P naught depend on? Doping. So, direct band-to-band recombination generation, their lifetimes, minority carrier lifetimes, they depend on doping. If you increase the doping, say if I increase the doping, what will happen? Tau will reduce. So, whenever you have a large doping, your recombination rate, that will increase. Okay, recombination will happen in smaller time. On average, the minority carriers will not be able to live. If you just say I have a very highly doped N-type semiconductor, and if I throw some minority carriers into it, they will disappear very quickly, very quickly, because this. If I have holes and I increase this N naught to very high, say 10 to the power 20 per centimeter cube, tau will become very small. This will die very quickly. Exponential of minus t to the power tau is small, exponential to the term which is a large negative number, it will die very quickly. Okay, so the plot will be something like this. So this is delta P as a function of time. Tau decides how quickly or how later it will decay. Okay, so we talked about the direct band-to-band recombination. Let's talk about indirect thermal recombination generation. Indirect means it's going to happen through mid-gap states. So let me show you a diagram, energy band diagram, and that will represent this indirect thermal recombination generation and what kind of processes can happen. So you have EC, EV, and then you have this ET. Let me assume that this is exactly in the middle, but it may not. Okay, it might be slightly above or slightly lower, roughly in the middle. I can have 4 different type of processes here. What processes can I have? I can have an electron. I can have an electron in the conduction band, and that jumps to the one of the trap states. Okay, so 4 transition processes. First is conduction band electron captured by a trap. So there is a conduction band electron and it is captured by one trap state. Capturing means it has filled that state. Okay, so something like this. Process A. There can be a process, another process. This captured electron can go back to the conduction band. That's a possibility. Yes? In this process, it releases the energy. In that process, it will take some energy and will go back to the conduction band. It is possible. So, electron release from the trap state to the conduction band. like this, process B. There can be another process. So this electron came down here, now it is filled, there is a filled state, and the electron in the filled state goes to an empty state in the valence band and recombines with the hole. So that's the process. Electron release into an empty valence band state, right? So when electron is released into an empty valence band state, it is equivalent of saying that the hole has come to a state, a filled state at this level. Okay, release of electron from here to here is equivalent to saying that a hole has moved up here. When electron leaves it, so it leaves an empty state. Empty state means a hole, right? So this, either you can say that electron has come from here to here, or you can say the hole has gone from here to here. Both are the same thing. There can be one more process in which the electron in the conduction band can transition to an ET level. Okay, process number 4. A valence band electron is captured by a trap state. Or equivalently you can say a hole has come down here. Electron going from here to here is equivalent to a hole going from here to here. So this. So there can be these 4 possibilities, and all of them are going to contribute to this recombination generation process. Okay. Okay. Now let's try to derive some results. Let me say NT is the total trap concentration. Total trap concentration means number of traps per unit volume. So that is the total trap concentration. Let NT be the trap concentration which is filled. So it is the filled trap states, concentration of filled trap states. Some of them will be filled, some of them will be empty. So NT, small nt is the concentration of filled trap states, and PT is the concentration of empty trap states. And of course, NT plus PT will be equal to capital NT, total number of states. Now I am going to calculate the rate at which these processes happen. Now always remember, the rate is equal to some proportionality constant times the carrier concentration in initial states, the available carrier concentration in initial states, and times the available state concentration for the transition. Okay, what we have initially, the particle concentration, and what kind of state is available. So state concentration, the product of that will be the rate, as we did in case of recombination rate in direct band to band gap. Yes, initial concentration of carrier, it can be electron or hole, final concentration of state. Now let's try to calculate the rate of change of concentration in the conduction band. Now which of the processes are changing the electron concentration in the conduction band? Which of them are changing the electron concentration? A and B. So in A you release an electron, right, and in B you capture an electron, but both are connected with the conduction band. Yes, these processes, they don't directly affect the conduction band electron concentration, because this is a transition between ET and EV, nothing to do with this. Okay, indirectly they can affect, but directly no. So the concentration of electron, rate of change of concentration of electron in the conduction band is going to be equal to the change in concentration of electron because of the process A plus rate of change of electron concentration because of the process B. Yes? What is the rate of change of electron concentration because of the process A? What will it depend on? So you have some electrons and you have some empty states. So it will depend upon it will be proportional to the product of electron concentration in the conduction band, which is N, and number of vacant states in the ET level, number of available trap states. Yes, empty states. So del N by del T is a product of N and PT. PT is the available state, empty states, concentration of empty states. And Cn is the constant of proportionality. And I have a negative sign here because the process A will reduce the electron concentration. If electron comes down from here to here, concentration of electron is reducing here. So that's why I have a negative sign here. Okay, what about the process B? What about the process B? And by the way, this Cn is called capture coefficient. C stands for capture. So capture coefficient for the process A, of the electron. N means for electron. It means the Cn will determine how effectively a trap can capture an electron. So that's the capture coefficient. Okay, it will of course depend upon the type of trap you have, its Coulombic potential and everything. Okay, so what about the process B? Now process B is increasing the electron concentration, of course, but what will it depend on? Number of, see here, carrier concentration in initial state. So what is the concentration of electrons here? What is the concentration of electrons here? Concentration of electron is the same as the concentration of filled trap states. If they are filled, they have electron, right? Filled trap states means they have electron. So it will be definitely proportional to Nt, small nt, times the concentration of empty states in the conduction band. Now, conduction band is, it's the only a small fraction of conduction band is filled. Almost all of the conduction band is empty. Yes, conduction band is empty, almost all of it is empty. So now think from this perspective. If I have this recombination generation going on, right, some back and forth going on here, will that affect the number of available empty states in the conduction band? Yes, it will, but not by a very large amount. You have a lot of empty states in the conduction band. Say some of them are filled by this electron concentration, a small fraction of this. So will that change the number? If I have this back and forth going on, yes, there is some change in the electron concentration happening, but does it matter? No, because there are so many other empty states which are available. So the overall number of empty states that are available for this electron to go here, they are not changing throughout this recombination generation process. Over the length of this process, this number remains a constant. So I have proportionality. In proportionality I will have Nt, but this proportionality factor, it's not changing throughout this recombination generation process, so that will be a constant. And then you have a constant of proportionality. So there are two constants, they will make another constant. So I have this. So this is only proportional to Nt, because that other thing, that other constant is embedded into this En. Why the term E? Because this is emission of electron in the trap state into the conduction band. So that's why this is E, and N stands for electron emission. This is called emission coefficient. Okay, and I have a positive sign here because this process is going to increase the concentration of electron in the conduction band. That's why positive. Okay, now let's talk about these two other processes, and let's talk about the concentration of holes in the valence band. So which are the processes that affect the concentration of holes in the valence band? Process C and D. So process C, the holes are going from valence band to the trap level, and for process D, holes are coming back. Okay, so the rate of change of hole concentration, del P by del T. Rg means recombination generation process. I thermal means, okay, so there has to be an I here. Okay, I thermal means indirect thermal recombination. Okay, so net rate of change of hole concentration is equals to del P by del T due to C plus del P by del T due to P. What is del P by del T due to C? So in C, holes are going from valence band to the trap states. What kind of trap states are occupied by the hole? See, electron wants to go to an empty state, hole wants to go to a filled state. If there is an electron here, that is going to attract this hole. So hole goes to a filled state. I mean, you can think in terms of electrons as well. So there is this electron concentration here and there is this empty state concentration here. So empty state concentration is the hole concentration and electron concentration is the filled state concentration. So this process is proportional to the concentration of filled states here into the concentration of empty states here. What are the empty states? The concentration of hole. So what do you get? P times Nt. Nt is the filled concentration in the traps, P is the hole concentration. And then you have Cp, capture coefficient for hole. And you have a minus sign. Why minus sign? Because when electron comes down here, it annihilates a hole. So it reduces the hole concentration. So that's why there is a negative here. Let's talk about the process D. So process D, in the process D, hole comes from ET to EV, or an electron is going from here to here. Now, what will this rate depend on? There are a lot of electrons in the valence band. Throughout the recombination generation process, the concentration of electrons in the valence band, it is not changing. It's changing, but it's not changing much. Even if some of the electrons are transitioning to say some other energy levels, so this concentration is not going to change. So this is almost a constant. So that constant number times the number of available states here. So what is the number of available states here for an electron? Pt. Okay. So it is proportional to only Pt. It is also proportional to the number of states here, or number of electrons here, but that is almost constant. Okay. So Ep is the emission coefficient for hole. So the process is basically emitting the hole from the trap state into the valence band. If electron is going from here to here, hole is coming from here to here. So this process is emitting the hole from the trap state, that's why it's an emission process, and this process increases the hole concentration here. If electron goes from here to here, it creates more empty states here. So that means the hole concentration is increasing. So that's why there is a plus sign. Okay, now you know the rates for all of these four processes. So what's the next step? What do I do now? Let's try to see how these coefficients are related to each other. How they are related to each other can be determined from the equilibrium situation. Now in equilibrium, what will happen? In equilibrium, del N by del T, it is going to become equal to 0. Yes, the electron concentration will not change in the conduction band and hole concentration will not change in the valence band. So del N by del T, this quantity will be equal to 0, and del P by del T, the total one, the net one, that will be equal to 0. This is still not equal to 0. I mean, these two are not 0. But the sum of them is equals to 0. Similarly, these two are not 0 individually, but the sum of them is equals to 0. So what do we have? We have in equilibrium this del N by del T Rg I thermal is equals to 0. So if I make it equal to 0, it means this is equals to the minus of this. Okay, so this is going to be related to this. Yeah, so En into Nt will be equal to Cn into N into Pt. So En equal to Cn n Pt divided by Nt. Now these knots are because I am talking about equilibrium. Okay, equilibrium concentration of the filled trap states, equilibrium concentration of the empty trap states, equilibrium concentration of electrons, equilibrium capture coefficient, equilibrium emission coefficient. So all of them are related like this. Further, if I make del P by del T equal to 0, so that will give me EP naught, relationship between E emission coefficient for the holes and the capture coefficient of the holes, right, and the hole concentration, NT naught, PT naught. That's what I will get. So all of these coefficients are related. Now I will make some assumption. To simplify things. The assumption is that these coefficients Cn, En, Cp, Ep, they are not changing much throughout this recombination generation process. This is what my assumption is. So capture coefficient and emission coefficient, they are not changing much throughout this recombination generation process. It means their value will remain approximately close to their equilibrium value, meaning En is equals to En naught, Ep is equals to Ep naught, Cn is equals to Cn naught, Cp is equals to Cp naught. Plus one more assumption. The concentration of filled state and concentration of trap state, concentration of filled states is NT naught, concentration of empty states is PT naught. I am assuming that under the assumption of low level injection, these values also do not change much throughout the course of this recombination generation process. So they will also remain equal to their equilibrium value. This is my second assumption. It means PT at any point of time will be approximately equal to PT naught, and NT at any point of time will be equal to NT naught. They will change, but the change will not be much if I am talking about the low level injection. Low level injection means my delta N and delta P, which are created here and here, they are not very large quantities. Okay, so whatever the concentration of filled and trap states was there in thermal equilibrium, I am assuming that even during this recombination generation process, that remains the same. So after making these assumptions, what do I get? This En naught will become En, Cn naught will become Cn, N naught, I will keep this N naught as N naught. I am not assuming N naught is equals to N, but PT naught is PT, NT naught is NT. So this is what I get. En is equals to this and Ep is equals to this. So what do they now mainly depend on? En depend on the concentration of electrons in equilibrium. Ep depends upon the concentration of holes in equilibrium, and of course the trap states. Okay, I'm not assuming that N naught is equals to N. Of course N changes appreciably. N or P, these quantities will change appreciably, so these cannot be assumed as constant throughout the thermal recombination generation process. Okay, now because I have this relationship, so if I use this equation number 3 into my equation number 1. So what was my equation number 1? So that was the equation which was del N by del T Rg I thermal is equals to the total rate, the sum of the electron concentration change due to the process A plus the sum due to process B. So that will become equal to this. Okay, this first term is coming from the process A minus Cn into N into Pt. The second term, which was En times, if you remember, so this was proportional to so del N by del T. So this is covered. The second one was proportional to, because electron was going from the ET to the conduction band, so that was proportional to the number of filled states here, which is NT, and because there are so many empty states here, so that became constant. So this was this, right? Now this En is this. You put your En here, so that will be Cn, you can take out, so Cn is here, and then you have this N naught, PT, NT, and this NT is still here. So this is going to get cancelled, NT, right? And you can take this CN is already out, so what do we do? So we can take this PT out, right? NT is cancelled, so PT we can take it out, so it will become minus CN into PT into delta N, because you will be left with N minus N naught here. N minus N naught is delta N. Yeah, that's what you get. Cn into PT, empty states, into delta N. Now let's assume that I have a p-type material. In the p-type material I have large concentration of holes and electrons will be in the minority. I will always be talking about the minority. I'm talking about del N by del T. So what will be the material for which this concentration of electrons, that will be minority? It will be p-type material. Okay, so let me assume a p-type material. In the p-type material, I know that the Fermi level is below my ET, because ET is somewhere in the middle, and the Fermi level, I know that in the p-type material it is close to EV. So what will I get? Because EF is smaller than ET, right? So where is that figure? Oh yeah, here. So this figure, look at this figure. EC, EV and EF is somewhere here, and you have these ET. Now EF is smaller than the ET. Can you tell me, will these trap states will be filled or empty? Fermi level. What is Fermi level? Fermi level is on average, what is the energy of an electron? And Fermi level decides what kind of distribution the electrons will have. After the Fermi level, the probability reduces. Probability of occupancy reduces after the Fermi level. Below the Fermi level, there is a lot of probability of occupancy. If my Fermi level is here, what will be the probability of occupancy of these traps? Low. It will be low, because Fermi level is smaller than the ET. I have an energy level which is larger than the Fermi level. Okay, so probability of occupancy of that level is going to be small. So the concentration of these states being filled by the electron, the probability of that is going to be small. So the concentration of electrons in these levels are going to be very small for a p-type material. It means most of these states will be empty. Let me equate that number to the total number of states, because see, PT plus NT is capital NT and small nt is small, so PT is approximately equal to capital NT. Yes, I am neglecting the number of filled states here, which is very small for a p-type material. Okay, now PT is approximately equal to NT. Now look at 5. So this PT, I can replace this with NT. So what do I get? So I get del N by del T, the net rate of change of electron concentration in a p-type material because of the indirect thermal recombination, is equals to minus delta N by tau N. This thing, the inverse of this thing, I have written it as tau N. Tau N is equals to Cn into NT, because PT is approximately equal to NT. So this is again some kind of a minority carrier like that, but the process is different. Whether you have a direct band gap recombination generation or indirect band gap recombination generation, the form is similar. There also we got delta N divided by tau. Here we are also getting delta N divided by tau, but those tau may not be the same. It should be 1 over this. That's why it's, yeah, because this NT should reduce this tau N. Okay, so this was 1 over this, because this is NT, and yeah, so this should be 1 over. Okay, so when I have a lot of traps, it will reduce, and when I have a large Cn, it will reduce. Similarly, for an n-type material, I can deduce similar conclusions for the holes, because holes will be in the minority. I can derive using the similar argument, and in that case my EF will be greater than the Fermi levels. So the EF is going to be somewhere here. If my EF is here, most of the states will be empty or filled. Most of the trap states will be empty or filled, because on average you have a larger electron energy and they can go down to these states and reduce their energy. So most of these states will be filled. So your NT will be approximately equal to capital N. And PT will be approximately 0 or negligible compared to these quantities. So in that case, what do you get? You get minus delta P. This is not tau, this should be tau P. Okay, and tau P will be equal to inverse of Cp times Nt. Again, if you have a larger capture coefficient or a larger trap concentration, that will reduce the tau. Okay, so this is under the assumption of low level injection. Whenever you have a low level injection, you can make all of these assumptions and derive very simple relations. Now, what about a case which is generic, when I don't have a low level injection or any level of injection, right? It can be low, it can be high, it can be somewhere in between. What is the relationship? So for that, let's go to the next slide. Indirect thermal recombination generation for a general case. I'm not going to derive it. In fact, the derivation is somewhere I left in between. If I had completed that derivation fully and did not make that assumption, I would have reached the expression I'm going to show. But that is more involved, and so I'm going to skip the derivation, but you can follow Advanced Semiconductor Physics by P-Rex, and the derivation is there. So finally, what do I get for any generic case is this. A generic case in the steady state. Steady state means you don't have quantities that are changing with time. So if you have, say, trap concentration, right? Filled trap concentration is NT or empty trap concentration is PT. That is not going to change with time. So that is the steady state. By the way, steady state is not equal to equilibrium. Equilibrium is different. In equilibrium, you can't have any current. In steady state, you can have a current, but all the processes are balanced by their opposite processes. So if you have the electrons coming to fill these traps, there are electrons going from here to the valence band, and those rates are equal. So that's why the concentration of filled states or the trap states, they are not changing. Okay, you have constant capture and constant release, and the release and capture, their rates, they are equal. Okay, so in that case, del N by del T or del P by del T, both will be equal, right? The rate at which the electrons are getting annihilated or the holes are getting annihilated or they are getting generated, both of them will be equal. Yes, because of the pairing, it is equals to Ni square minus Np divided by tau P into N plus N1 plus tau N into P plus P1. Now what is this N1 and P1? N, of course, is electron concentration, P is the hole concentration, Ni square you know, minus Np, right? What about this N1 and P1? So N1 and P1 depend upon where my traps are located with respect to some energy level. So what is my N1? N1 is equals to some Ni. It looks very similar to your electron concentration and hole concentration expression. So N1 is equals to Ni into e to the power Et minus Ei by Kt. Et is the trap level, Ei is the intrinsic level, right? The middle. So how far my trap is from the middle of the semiconductor band gap, that decides my N1. if it is too far, if ET minus EI is too far, then N1 will be large. If ET and EI are close, then N1 will be small. And because it appears in the denominator, okay, so it will have opposite impact. So if my N1 is small, then these rates will increase. Okay, so it means these mid gap levels, if my ET is equals to EI, so N1 will be the least possible value. Of course, for the cases where ET remains greater than EI, of course ET can go negative also, right? ET minus EI can become negative, but so N1 will become equal to Ni. So in that case, this will increase a lot. It means the mid gap states are very effective in changing the concentration of electrons and holes. That's why I'm always talking about mid gap, right? Because they are the most important states. Okay. Similarly, you have P1. P1 is equals to Ni into e to the power minus of Et minus Ei by kT. This formula, this is also called Shockley-Read-Hall SRH recombination generation formula. So whenever you say run a TCAD, in the physics section you have to specify this recombination generation model. This is the model that is usually used in the TCAD. SRH recombination. Okay, Shockley-Read-Hall. Of course, the name of the scientist, Shockley-Read-Hall. Now, using this, I can derive whatever expression we derived. Okay, so for low level injection, whatever I have derived, right, del n by del t is equals to some minus delta n divided by tau n. Similarly for the holes, so that can be derived from here as well. Yeah, I'm going to quickly go through it. So before that, if I have Np which is less than Ni square, if the product of electron and hole concentrations, if it is less than Ni square, what will happen? Then it will become negative. Negative means del n by del t is negative. It means electron concentration and hole concentration is reducing. It means there is a net recombination that is happening. Okay, there is a net recombination that is happening. Similarly, if Np is smaller than Ni square, then there is a net generation that is going to happen. People who have gone through the p-n junction, in the forward bias, if you remember, the electron concentration and hole concentration in the depletion region, that increases, that is more than Ni square. N into P becomes greater than Ni square. That's why you have recombination and you have a corresponding recombination current. Similarly, when you have a reverse bias, so Np becomes less than Ni square, and then you have a net generation, so you have a generation current. So many of the times the current in the negative scale, right? So you have a positive voltage and negative voltage. Negative voltage current, which is almost a constant, that is also called generation current. It's coming from here. So we'll go there in the next class. I think we'll be able to start the p-n junction. Okay, so that's all coming from here. So I'm not going to go through how we can derive the similar relation. Yeah, so it's there in the notes. So, but the formulas that we derived, right? This equal to this and this equal to this. So they can be obtained from here using some assumptions. So those assumptions are listed here. Please go through them. I will not go through them again. Okay. So next is current continuity equations. Again, very important. When you are running a TCAD, you will always solve some of these equations. Current continuity. So what is current continuity equation? It's basically charge conservation. So what is charge conservation? It says that if I have a point in the semiconductor, the concentration of electron or hole that at that point, that is contributed by several factors. Okay, what kind of factors I can have there? So I can have some generation, recombination, yes, because of thermal. It can be direct or indirect. I can have some recombination generation because of light. I can have change in electron concentration at a point because of the transport also. Say this is the point and some of the electrons which were here transported here. That is also possible. What kind of transport there can be? Drift and diffusion. Because of the electric field, say some electrons moved from here to here. So that increased the concentration of electron here. Right? So that can be a factor. Similarly, if you have a diffusion, so say there was a larger concentration of electrons here and lower concentration here, so some of the electrons moved because of the diffusion from here to here. So that can also contribute to the electron concentration at that point. So change in electron concentration, net rate of change of electron concentration with respect to time at any point in the semiconductor is a combination of several factors. So the rate which is coming from drift plus the rate which is coming from diffusion plus the rate which is coming from say thermal generation plus the rate which is coming from any other process, say light or radiation or whatever. Okay, so this is the charge conservation basically. So if electron concentration is changing at a point, it has to come from somewhere. It cannot just appear out of the blue. Similarly, for holes, we have this. So let me try to calculate what is the value of this thing. So it's not very difficult to derive what is going to be the contribution of contribution to the electron concentration or hole concentration because of drift and diffusion, because of the transport. So let me show you a picture. So now say I have an electric field which is in this direction and I take a small volume of this semiconductor and say the length of that is delta x, the cross section area is delta A, and of course the electrons are everywhere, but let me focus on the carriers which are present in this small volume. Let the current at this end be Jx and let the current at this end be Jx plus delta x. It's a 1D problem. Right? I can extend it to 3D, but just for the simplicity. So current density at this cross section is Jx, current density at this cross section is Jx plus delta x. In general, they can be unequal. There is no reason for them to be equal always. They may not be equal always. Okay. Now, let me try to calculate the change in current from here to here. So what is the current? Current is charge this current density times area, right? So the change in current from here to here will be what? It will be delta is equals to delta Jn. N means I am talking about the electron current. So delta Jn times the cross section area, which is delta A. Current density into area gives me current. Change in current density into area gives me change in current. Now what is this quantity equal to? So delta Jn is of course Jn into x plus delta x minus Jnx. Yes. Times delta A. What is this quantity? Let's see. What will be this equal to? So I have a current which is entering. It means the charge is entering and then charge is leaving. So charge is entering at some rate which is J1. Charge is leaving at some rate which is J2. If those two are not equal, there will be some build-up of electrons. Yes, there will be some build-up of charge. Charge can reduce also, charge can increase also, depending upon what is my in and what is my out. If in is larger than out, then it will increase the electron concentration. If in is smaller than out, it will decrease the electron concentration. So it can change the electron concentration at a point. Now what is that concentration change? So what is the amount of charge that is there inside this? It is, let me call the electron density at this particular point, because it's a very small value, the electron concentration will not change much, right? So the electron concentration which is belonging to this whole volume is N, right? But N is number per unit volume, Yes, I have to multiply by the volume also to get the current. Okay, so times delta x times delta A. So that will be number into volume, that will be the total number here, times the Q will be the total charge here. Rate of change of that total charge has to be equal to current density change times area. Yes? Yes, this is the stored charge. The rate at which it changes has to be out minus in. So just take this delta in, delta x out. There is a partial differentiation here, so you can take them out. So this will be equal to Q into delta x into del n by del t. Delta you can cancel. Okay. So simply the difference will become Q into delta x into del n by del t, or you can say Jn into x plus delta x minus Jn divided by delta x is simply Q into del n by del t. Okay. Now what is my del n by del t drift plus del n by del t diffusion? It is equals to, for a particular point I will have to take a very small volume. So it means delta x will tend to 0 if I am talking about a particular point. Yes. So delta x tends to 0, and so what is this coming from? So this is that drift plus diffusion. Okay, what is it equal to? Jn x plus delta x minus Jn divided by delta x divided by Q. Delta x tends to 0. And what is the definition of this if delta x tends to 0? So this will be 1 by Q into dj by dx. So the buildup of electron at a particular point will depend upon the gradient of current. If there is a gradient in current, it means the current is not same. It means there will be some buildup of electrons. Okay, so that's what you have for the drift and diffusion, and your current continuity equations will of course you can write it in this form. So del n by del t will be that drift plus diffusion will give you the gradient term in J plus generation because of thermal plus other processes. Similarly for holes, you will see that there will be a negative sign here. If you derive it for the holes, you will find a negative sign here, djp by dx, right, plus the other terms. And this is for the 1D. In 3 dimension, this d by dx, actually this should be partial differential. It should be del by del x. Okay, it should be partial del. Okay, this del jp by del x, they will become equal to the gradient. Okay, so this gradient will become del dot j. So what is del dot j in 3D? Del j n by del x plus del j n by del y plus del j n by del z. So you'll have to take care of all the 3 dimensions in 3D. Similarly for holes. So this is usually what the TCAD does, especially for, if I am talking about 3D simulation, this is what the TCAD is doing. So let's stop our class here.